For today, I'm going to show you how to do problems where you have collections of objects that are, connected or pushing against each other in some way, and they're moving together as a unit. So the type of problem I'm going to talk about are ones like, let's say that you have two carts that are in contact. And there's a force applied this way. That force that's applied to the right cart is going to make the right cart accelerate, and it's also going to make the left cart accelerate, and those accelerations are going to be the same. Okay, let's give some values to this, and I'll show how to do this in the when I go through some example problems. So let's say that this is 5 kilograms, this is 10 kilograms, and let's say that this is 25 newtons, the force. And you can also have, similar things where, let's say it's carts again, but this time, let's say that they're connected by a cable. And I guess this time, well, I'll say that the right cart is being pulled this way with a force of 30 newtons. And let's say that this is 10 kilograms and 15 kilograms. Okay. And in both cases, let's say that what we want to know is the force that one of them applies to the other one. So for the pushing force, let's say, what's the force vector applied to the 5 kilogram cart by the 10 kilogram cart? And for the second one, let's say, what's the force vector applied to the 15 kilogram cart by the cable? Okay. So for these kind of problems, we're going to see that there's sort of a single approach that, there's something that they have in common. And that is that in almost every case, any case where you're not given the acceleration of these bodies beforehand, the first step is to isolate the whole collection of objects together and calculate the acceleration. So the approach is first, we're going to isolate the whole system. And from that, we're going to calculate the acceleration. And then second, we're going to isolate an individual body. Okay, so I'm going to do both of the two example problems above, and I want you to look for this approach as I'm doing it. I'm going to start by isolating the whole system, find the acceleration, and then I'm going to isolate the individual body, and I'm going to use the acceleration that I got in the first step. Okay, so for the first example, I'm going to do the one that I drew right up here with the 5 and 10 kilogram and the 25 Newton force. Okay, so this one is 5 kilograms. The other one is 10 kilograms. And there's a 25 Newton force pushing to the left. And we want to calculate the force vector on, what did I say, on the 5 by the 10. Okay, so the first step is we're going to isolate the whole system. And so I'm going to draw a free body diagram of the whole system. there's a weight force. The total mass of this system is 15 kilograms, so the total weight force is that times 9.81, 147.15. There's a pushing force up from the ground that I'll call N, I'll call it W for whole. And then the only other force on the boundary besides that pushing force is the 25 Newton force going this way. That's a complete free body diagram. So now I'm going to go to Newton's second law. And there are three forces in the free body diagram, so we have to do three forces in the Newton's second law. If I use a standard coordinate system like this, then that pushing force is 0, positive N whole, plus the weight force is 0, negative 147.15. The 25 Newton force is in the negative x direction, so plus negative 25, 0. And that's equal to the total mass times the acceleration. And since this is rolling along the x-axis, we know the acceleration is only going to have an x component. So I'll write it as a0. And this is a case where that acceleration is going to come out to be negative, but we don't have to decide that now. We can put it in like this, and the sign is going to come out and give us that answer out of the math. Okay, so the x component of this equation says negative 25 is equal to 15a. And so a is equal to 1.6 repeating meters per second squared. I forgot the negative. Negative 1.6 repeating meters per second squared. And then if we wanted that normal force, we could use the y equation. There's nothing that we're asked for in this problem where that's going to come up, but we know it from this. Okay, so now we have the acceleration, but that's not what the problem asks for. It asks for a force that's applied to one of these bodies by the other one. And so what I'm going to do now is I'm going to isolate it really doesn't matter which one because the magnitudes are the same. I guess I'll isolate the 5 kilogram cart though. So I'm going to isolate the 5 kilogram cart, knowing now that its acceleration is the same as the whole system. And I'm going to use that to calculate that pushing force from the 10 kilogram cart. So a free body diagram of the 5 kilogram cart. There's a weight force of 5 times 9.81, so 49.05. There's a pushing force of, I'll call that N5, that's the normal force on the 5. And what else? Well, there's no 25 Newton force because that's acting on the 10 kilogram cart. So the only force is the pushing force from the 10 kilogram cart. And that's this way because it's a pushing force. And I'll call it R. You could call it N2 or something if you want, but doesn't matter. It's just a variable name. And now we'll go to Newton's second law. I have to put in all three of these forces. So the first one is 0, negative 49.05. The second one is 0, positive N5. Third one is negative R0. Three forces in the free body diagram, 3 in Newton's second law. So now we just have to deal with the mass times the acceleration. The mass of our new system is 5. And the acceleration vector is what we get from substituting negative 1.6 repeating into this acceleration vector. Okay, and so that's negative 1.6 repeating, 0 for y. The x equation says negative r is equal to 5 times 1.6 repeating, which is 8.3 repeating, negative, so 8.3 repeating. And so what we get is that this variable r is equal to 8.3 repeating newtons. That vector that's shown in the free body diagram is the force on the 5 by the 10. And so the force on the 5 by the 10 is equal to, you can plug this variable into this force vector and you get negative 8.3 repeating 0 newtons. Or another way to think of it is the magnitude of this force is 8.3 repeating. Plug it into, or that force is applied in the direction shown by the arrow in the free body diagram. And so it's a force this direction with a magnitude of 8.3 repeating newtons. Okay, so let's see how this works on one where the two are connected and they're being pulled. So one is pulling on the other one. This first example was one where they're pushing on each other. Okay, so we'll go up to this one where we have a 10 and a 15 kilogram connected by a cable. It doesn't have to be a cable. It could be some other kind of coupler. And there's a 30 Newton force pulling it to the right. What was that, 10 and 15? Okay, so we have one there. That's 10 kilograms. And the connector. And then there's the 15 kilogram. And the 15 kilogram cart is being pulled to the right with a 30 Newton force. And I said up here that what we're going to try to calculate is the force to the 15 by the cable. Okay, so the cable I'm talking about is this middle cable, and we want to know the force applied to the 15 kilogram body. Okay, well, this is one, again, where we have two objects whose motion is the same. It's a collection. And so what I'm going to do is isolate the whole system together, calculate the acceleration of the system, and then isolate the 15 kilogram using the acceleration that we just found. Okay, so a free body diagram of the whole system. Okay, the total mass is 25. So we have a weight down of 25 times 9.81, so 245.25. And then we have a total pushing force. So I'll call that, I guess like the other one, I'll call it N sub W for the whole normal force, the pushing force on the whole system. And then we have the 30 Newton force going this way. So Newton's second law says 0 NW plus 0, negative 245.25, plus, in this case, that 30 Newton force is in the positive x direction. And all this is equal to the total mass of the system times the acceleration. We know that these are rolling along the x-axis, so I'm going to write this as a0, and we're going to try to find that a. The x component of this equation says 30 is equal to 25a, and so we get that a is equal to 6/5, which is positive 1.2 meters per second squared. And to get the acceleration vector, we're just going to take this and plug it into that vector. And so the total acceleration this time is positive 1.20. Now that we have that, I'm going to isolate the 15 kilogram cart. Now the system has a mass of 15, so the weight is 15 times 9.81, so 147.15. There's a pushing force, but it's not the same as the pushing force on the whole system. It's just the pushing force now on the 15 kilogram cart. So I'm going to call that N15. There's a pulling force from the cable that connects these two. Because it's a pulling force, it goes this way. And I'll call that T. And that's the force we're looking for, this force vector, the force applied to the 15 by the 10. And then the only other force is the 30 Newton force pulling it this way. So there are 4 forces. And so we have to put all 4 of those, not in the free body diagram, in Newton's second law. So we have negative T0 plus 0, negative 147.15 plus 0, N15 plus 30, 0 is equal to 15 times the acceleration vector. And now we know the acceleration vector is 1.20. So the x component of this equation says negative t plus 30 is equal to 15 times 1.2. I guess that is 16, right? 15, 18. Yeah. So 18. And so now you do the algebra to solve for t. You get t is equal to 12 newtons. And now, like before, we're looking for this force. So you can plug this t value in there. And you get that the force on the 15 by the 10 is equal to negative 12, 0. Or another way you can think about it is the magnitude is 12 newtons, and the direction is the arrow as it's shown in the free body diagram. So this direction with a magnitude of 12 newtons. So that's the way that you approach these problems where you have a collection of bodies who all have the same acceleration. They're moving together.